Good evening, children. Today let us see the new chapter, that is states of matter. In this states of matter, I am going to start with the first topic, that is states of physical states of different substances and the extent of attraction between the particles of those substances. Particles means they can be atoms or molecules. Next, as far as the different states of matter are concerned, we have solid matter, liquid matter, and then the gaseous matter. So, the topics or concepts are like this: different physical states of matter. Next, interaction between the particles of the matter, that is predominance of intermolecular or interparticle interaction and thermal energy. And then we'll move towards the interactive forces. Means we can say the bonds. Bond means interaction between the particles, that is attraction, right? Which keeps the particles together. So, interactive forces are types of forces interactive forces, they can also be called as, right? Now let me start with the different physical states of matter. First, let us see what is meant by matter. It can be anything that occupies space, exerts pressure, and felt by any one of our sense organs, like skin, nose, etc. So, anything that occupies space, exerts pressure, and felt by any one of our sense organs, that is called matter. And this matter is divided mainly into three types based on the type of interactions between the particles of the matter. And those three different types of matter are: number one, solid matter; number two, liquid matter; and then number three, gaseous matter. Now, let us see in the case of solids, liquids, and gases. Predominance of interaction means order of interaction. When we move gas to liquid, liquid to solid, whether interactive forces between the particles increases or decreases. Same way, when we move from solid to liquid and liquid to gas, predominance of thermal energy means the order of thermal energy, that means the energy required for motion of the particles, free movement of the particles, that is called thermal energy. So how much energy we need to give to make the particles of a particular matter, solid or liquid or gas, to move freely, that is said to be thermal energy. And always interactive forces between the particles is, for example, solid if you take, in between the particles of the solid matter, attractive forces are maximum, very high. Therefore, thermal energy which is required to make the particles to move freely is very, very high. If attraction is more, then energy required to make the particles to move freely will be more, because we need to give more energy. Right? So in that way, we can show in the form of diagram like this. So here gaseous matter, next comes liquid matter, and then solid matter. So head of the arrow mark shows that when we move gas to liquid, liquid to solid, the molecular interaction or the interaction between the atoms, or in general you can say interparticle interaction increases. So we can write here predominance means increase. Predominance in interparticle attractive forces means in the direction of head of the arrow mark, this, as we go, interparticle attractive forces increases. In the case of gaseous matter, particles fly far away from each other. So attraction between gaseous particles is very, very less. That is why gases exhibit the characteristic property of undergoing expansion. Means very small amount of gaseous matter can occupy large volume. That is the point. Next, when we move from gas to liquid, attractive force between the particles increases. Means free spaces between the particles of the liquid becomes less. So free movement of the particles decreases when compared to gas. Again, when we move from liquid to solid, in the case of solid, all the particles are arranged in a particular pattern where there is no lacuna or free space or void, V-O-I-D. It is also called cage, C-A-G-E. In chemistry, cage means free space. Between the particles of solid matter is very, very less. Almost zero we can see. Means interaction between the particles of the solid matter is maximum. That's why it is written predominance in interparticle attractive forces in this direction. Now let us see thermal energy. It is quite opposite. Now solid, liquid, and here gas. Now, in this order, that is quite opposite to the first one. When we move from solid to liquid or liquid to gas, the thermal energy, that is energy required for the free movement of the particles, increases from solid to liquid, liquid to gas. Right? So energy required, order of, we can write order amount of energy required for free movement of particles. So that increases in this order. So in general, you can say in the case of solid matter, particles are arranged very tightly with each other without leaving empty spaces, whereas in liquid substances, free spaces are there to small extent between the particles, whereas in gaseous matter, empty spaces are enormous. Therefore, they exhibit the characteristic, the properties like attractive forces between solid matter is very high. That is why there is no empty space. Right? Attractive forces in the case of particles are the liquid matter are slightly less when compared to solids. That is why we have empty spaces between the particles of the liquid. That is why liquids can be compressed to small extent. And when we move to gaseous matter, empty spaces are enormous. Particles are lying far away from each other. Therefore, free movement of particles in the case of gaseous matter is possible to the maximum extent. So, attractive forces between the gaseous particles is minimum. So, that's about matter, types of matter, and the relationship between the attractive forces between the particles and free movement of the particles. Right. Now let us see types of bonds. To what extent the capacity to form the bonds between the particles varies. So types of bonds. We have varieties of bonds like van der Waals attractive force, and then hydrogen bond, is a different type of what do you call dipole-dipole attractive force. That is nothing but hydrogen bond. Next, apart from this, we have different types of attractive forces built between the particles, like dispersive forces. Next, dipole-dipole attractive forces. Next, dipole-induced dipole. These are the different types of attractive forces built between the atoms as well as the molecules of matter. Now let us see those one by one. First one is dispersive forces. Dispersive forces. Now let us see what is is meant by dispersive force. How these forces keep the particles close to each other. Imagine there are two atoms, atom A and B. Center part of both the atoms A and B are positively charged, and negative charge is distributed equally around the center part of both the atoms. Means symmetry is there in distribution of negative charge. It can be understood in this way. So this is atom A, and this is atom B. These are two atoms. So this is atom A and this is atom B. And as I told you, the center part of atom A is positively charged. So also center part of atom B is positively charged. Now around these positive charges we have electron density, and these electrons are equally distributed throughout the bulk of the atom. Therefore no atom has any charge. First time scientist, German scientist London is named. He proposed that any atom for a moment can develop positive charge at one of its ends and negative charge quite opposite to its end. Means atom can have two charges for a particular moment. Right? This was proposed by London. That's why these dispersive forces are also known as London forces. Right? If atom A undergoes for a particular moment a change wherein its one end develops, means positive charge, it will be delocalized. It gets moved to one end and the negative charge to the other end. Same way, the other atom develops positive charge at its one end, means it is delocalized, center part to one end. The other end will have negative charge. So this is atom A and this is atom B. Now quite opposite charges, negative and positive, they begin to attract. That type of interaction is called dispersive force. And see this end, and in the case of atom B, this end refers to negative density or electronic density or negative charge. So those two atoms come opposite to each other with their quite opposite charges. That will keep those particles close to each other. In this way, the charges can be aligned, or it can be in a different way like this. Imagine those two atoms, once again, atom A, atom B. See, in this diagram, positive charge moved towards left hand side, LHS. Imagine if positive charge could have moved towards right hand side and entire negative density could have moved towards the other end of atom A. Same way, in atom B, positive charge towards one end and negative charge towards left hand side. In this way also, the positive charge of atom A can attract the negative charge or the electronic density. So this can be labeled in this way. Negative charge or electrons. Now these two particles can attract each other. So in that way, the particles or the matter, if that matter could have made up of atoms, those particles can attract each other in this way. Right? Next, the distance between these two particles, this distance, is symbolically represented by R. Right? The attractive forces between the particles is inversely proportionate to 1 by R raised to 6, where R stands for the distance between the particles, like particle A, particle B, right? Or atom A, atom B, and so on. That's about dispersive forces, how they keep the particles close to each other. Okay. Now let us see the second type of attractive forces, that is B. Dipole-dipole attractive forces. Now let us see what is meant by dipole. Di means two, pole means ends or terminals. This attractive forces, this type of attractive force was observed in the case of such matter which is made up of molecules. Best example for this is hydrochloric acid. That molecule we can show in this way. This is hydrochloric acid molecule. In this molecule, one end hydrogen atom, the other end is occupied by Cl. Just to understand the concept. Now, these two are known as poles, ends, terminals. All this means same. Next, hydrogen and chlorine. The electronegativity values are different. Hydrogen can lose electron very easily even though it is gas. It exhibits the property similar to metals. Right? So like metals, hydrogen exhibits electropositivity. Next, chlorine is more electronegative in nature. So it exhibits electronegativity. Electropositivity means tendency to give away electron, to lose electron. Electronegativity means it is the property or tendency of an element to gain the electron. So in that way, hydrogen will develop partial positive charge. This is one molecule of hydrochloric acid. And this is dipole in nature. It is polar molecule because it has two poles. Hydrogen develops little positive charge and chlorine develops little negative charge. We read this sign as delta. In chemistry, we read this as delta. There is one more sign, that is triangular sign. That is also delta. And we use this triangular sign in the case of heating processes, particularly in the case of equations. Right? In endothermic reactions, they occur with the absorption of energy. In such reactions, when we are required to represent entire change in the form of equation, there we write delta, this delta, triangle sign for heating. And above this delta we use to represent charges. This is polar molecule because it has two poles, positive pole and negative pole. Right? So this is completely one dipole. Like that, imagine there are two HCl molecules like this. Right? And this is one HCl molecule, this is other HCl molecule. And hydrogen atoms in both cases have partial positive charges. One more thing. Delta stands for partial here. Partial means little. In English dictionary, partial has a different meaning. Right? In chemistry, partial means little. So this molecule develops a little positive charge at one end, little negative charge at the other end. In that way, both the molecules of HCl, when they phase in such a way that the positive pole comes close to the negative pole, then they start attracting each other. Now, reverse is also possible. Means one HCl molecule and the other HCl molecule. In this way, one molecule of HCl may have partial positive charge towards right hand side, partial negative charge towards left hand side. Same way, the other HCl molecule can have partial negative charge towards left hand side and partial positive charge towards right hand side. In this way. Now also attraction is possible. The only thing is elements with their charges, their positions are changing, but opposite poles are lying close to each other. Then also they attract each other. Characteristic property of this type of attractive force, that is dipole-dipole attractive force, is it is stronger than dispersive forces. Right? Next, here the molecules may be stationary. These HCl molecules may be stationary. Stationary means they are not moving, they are stable. Next, these HCl molecules may also be rotating in nature. Right? Rotating means movement should be there. One should be stationary case, the other one should be rotatory case. If the molecules are stationary, if dipole are stationary, then the interactive force may. Now children, let us see dipole induced attractive forces. Dispersive forces, dipole-dipole forces over. Now the third one is dipole induced forces. It means there will be a permanent dipole with two opposite poles. Opposite poles in the sense positive pole and negative pole. Right? It's a permanent dipole and it will have a particular dipole moment value. Dipole moment means distance between the two poles of opposite charges multiplied by any one of the two charges, positive charge or negative charge. That is equal to dipole moment. Right? Now, permanent dipole, in the sense that molecule should have permanent two poles. And there must be one more molecule which has zero charge as a whole. Means it doesn't have two poles. No opposite two poles. The first molecule slowly it induces. Means it creates opposite poles in the other molecule. So, it is dipole induced forces. Dipole induced forces. In this, we have a molecule with two poles, means two ends. In this molecule, we have two atoms. So, one end or one pole is partially positive. Delta plus. Partial means in chemistry little. So, one pole will have little positive charge and the other pole little negative charge. So, this is a permanent dipole. Right? And this can also be shown in this way. This sign shows that this molecule has permanent dipole moment. Now imagine the other molecule. This is other molecule which doesn't have opposite poles, positive pole and negative pole. They are not there. Now the first molecule is going to induce. So we can say this is molecule without charges. Means no positive charge and no negative charge. Now what happens is, this molecule which has permanent dipole AB with partial positive charge, partial negative charge. Now this molecule, when it creates polarity in this molecule, and this molecule will become for a particular time a dipole or polar molecule, or it develops two opposite poles. Now this has become polar molecule because it has two opposite poles, positive pole and negative pole. Now in one molecule, one pole has negative charge, in the other molecule the other pole or end or terminal has positive charge. Now this negative and that positive charge, they begin to attract each other. This is called dipole induced forces. Forces means interactions, means attractive forces. Interaction can also be a repulsive force. That will come little later. Once again, dipole induced forces refers to a permanent dipole or a molecule with permanent polarity, positive and negative poles. Right? Will have a specific dipole moment value. So in this case, this stands for dipole moment. Right? Here this molecule also, same molecule it is. Since it is a permanent polar molecule, so it has particular dipole moment value. That's about dipole induced forces. Next, there can be a second type of interaction, that is called repulsive force or repulsion. When is this possible? When two molecules with similar poles come opposite to each other, like positive pole, then they repel each other. Or when two polar molecules with similar poles, negative pole and negative pole, when they come close to each other, then they begin to repel each other. So it can be shown in this way. Imagine this is one polar molecule with two atoms in it, atom A, atom B. Atom A has positive charge, atom B has negative charge. Right? The other molecule which doesn't have polarity, it was induced by the first molecule which has permanent polarity. Then that molecule, if it develops charges, partial charges like this, partial negative charge, partial positive charge. Now, these two molecules will begin to repel each other. So, in between them, repulsive forces are operated. Right? In this case, attractive forces exist between the molecules. So there's about third type of forces, that is dipole-induced forces. Next, these attractive forces which are keeping the atoms close to each other or molecules close to each other, how do they affect boiling points and melting points? Boiling and melting points. Boiling point refers to a particular temperature at which liquid substance begins to enter into gaseous form. Right? Or we can also define boiling point like this: the temperature at which vapor pressure of a particular liquid matches with atmospheric pressure. This is called boiling temperature. Right? Same way, melting point refers to a particular temperature at which a particular solid substance enters into liquid form. Right? Or the temperature at which the vapor pressure lying on the surface of the solid, example ice, and the atmospheric pressure. See, in the case of boiling point, vapor pressure and atmospheric pressure, they are taken into consideration, like any liquid substance whose vapor pressure matches with the atmospheric pressure at a particular temperature. When we go on heat a particular liquid, its vapor pressure goes on increases. After a particular time, it matches with the atmospheric pressure. Then the bubbles are seen on the surface of the liquid, and that temperature is called boiling temperature. So, melting point, that refers to the temperature where a particular amount of solid substance at a particular temperature will enter into liquid form. And here in the case of whether that substance is liquid or solid, in between the particles, attractive forces, they exist and they keep those particles very close to each other. If we overcome those forces, then physical states of those substances, solid and liquid substances, changes. Here, in the case of liquid matter and solid matter, since attractive forces are existing, and those liquids are those solid substances which have very strong attractive forces, we require to give more and more energy to convert them into gaseous form or liquid form, if those substances are in liquid and solid forms respectively. So that's about boiling and melting points. Now, hydrogen bond. What is meant by hydrogen bond? Bond means attractive force which keeps the particles together. In the case of hydrogen bond, there must be hydrogen element. Besides that, there can be any element whose electronegativity is more than hydrogen, like oxygen, nitrogen, fluorine and chlorine. Right? Now let us see hydrogen bond in the case of hydrogen fluoride. Hydrogen fluoride or hydrochloric acid, or even we can take water molecules. They are also in between H2O molecules, we have hydrogen bonds. Right. Now, if HCl is taken, hydrochloric acid, in that we have hydrogen and chlorine. Chlorine is more electronegative than hydrogen. In water, H2O, oxygen is more electronegative than hydrogen. If you take HCl molecule, this is one complete molecule of hydrochloric acid. Next, this is other hydrochloric acid. Now, in between hydrogen and this chlorine, there is some attraction which is indicated by dotted line, and this is known as hydrogen bond. So in that way, hydrochloric acid means liquid, hydrogen chloride means gas, formula is same. So in the case of hydrochloric acid, we have uncountable molecules of HCl and they will have attractive forces in between them. That too, hydrogen atom of one acid and chlorine atom of the other acid molecule. And that hydrogen bond keeps the molecules very close to each other. This is one type of interaction between HCl molecules. Yes, children. Gas laws. These gas laws speaks about the behavior of gases. Behavior of the gases are controlled by the measurable properties like pressure, temperature, volume and quantity of gases. Quantity of gases refers to number of moles. Mole, the number of moles of the gas. Mole will be the quantity of the gas. So these are the four measurable properties which will affect the behavior of the gases. Based on these factors, we have what you call the gas laws, like number 1, Boyle's law, number 2, Charles' law, number 3, Gay-Lussac's law. Now let us see what do these laws speak about. Boyle's law speaks about the relationship between pressure and volume. Charles' law speaks about the relationship between volume and temperature. Gay-Lussac's law speaks about pressure and temperature. Right? There are certain measurable properties which remain constant in each case. Now, let us see Boyle's law. This is the first law among the gas laws, and this gas law, Boyle's law, as I said, it speaks about or tells the relationship between pressure exerted by the gas and volume occupied by the same gas. Right? And this can be stated like this. When temperature and quantity of the gas. Here quantity of the gas means number of moles of the gas, that is N. Small n stands for number of moles of gas. Right? So according to Boyle's law, when temperature and quantity of the gas remains constant, then the pressure exerted by the gas is inversely proportionate to its volume or directly proportionate to reciprocal of its volume. So this is Boyle's law. So it can be written like this. At constant temperature for a fixed mass of the gas, the pressure exerted by it is inversely proportionate to volume occupied by it. At constant temperature for a fixed mass of the gas, the pressure exerted by it is inversely proportionate to volume occupied by the same gas. This is the law. So according to this law, we can write P is inversely proportionate to volume, or P is directly proportionate to reciprocal of volume. Here condition is capital T means temperature on absolute scale and N remain constant, where T stands for temperature on Kelvin scale. If it is given in the numericals on Celsius scale, we need to add 273 or 273.15, and N is equal to number of moles. It means quantity of gas. Right? That is about Boyle's law. Now let us see, if we remove proportionality mark, what are we going to get? So according to Boyle's law, we know P proportionate to 1 by V. When this proportionality mark is removed, we will get a constant, that is P is equal to K by V. Or when we take V towards left hand side, then it will become PV is equal to K. Right? Say this is at a particular temperature. If we change the temperature, then pressure exerted by the gas, volume occupied by the same gas will also change. So here K is equal to a constant, or we can call it as proportionality constant. This is at temperature T. At temperature T1 and T2, we can write the equation P1 V1 is equal to P2 V2, and here PV is equal to K. At temperature T. So at temperature T1 and T2 we will have this expression, and this expression can also be written in this way: P1 by P2 is equal to V2 by V1. Now in this expression, if any three variables are known to us, for instance P2 we do not know, P1, V2, V1 are known, then the fourth unknown one can be calculated. So that way this equation is used. Suppose pressure P1 is given in terms of atmosphere and P2 is given in terms of bar. We should see that P1 and P2 both should be either in bar or atmosphere. Same way volumes. We should see that both the volumes should be either in liters or milliliters. Right. Now let us see the relationship between pressure and volume in the form of graph. Pressure values we are taking on y-axis, volume values on x-axis. Here pressure and volume both are inversely proportionate to each other. Therefore, we will get curves like this in the graph. In this way. So first curve is obtained. See, whenever the pressure values and volume values are taken on y and x axis at constant temperature, at each constant temperature we will get one curve. This curve, imagine it is obtained at 200 Kelvin. The other curve is at 400 Kelvin. Third curve at 600 Kelvin. Means at each constant temperature we will get curve when pressure and volume values are taken on y and x axis in the graph. Therefore, these curves are known as isotherms. They are called isotherms. Isotherms. Iso means similar. Therm refers to temperature. So isotherms means curves obtained. Obtained in the graph at constant temperature when pressure and volume values are taken on y and x axis respectively. So in MCQ you may be asked isotherm concept. Iso means similar, same or constant. Therm refers to temperature. So that's about the relationship between pressure and volume. Now let us see, instead of pressure and volume, if we take pressure and reciprocal of volume, then what type of graph we are going to get? Let us see. According to Boyle's law, pressure is inversely proportionate to volume or pressure is directly proportionate to reciprocal of volume. So keeping that in the mind, if the graph is drawn, right, on x-axis we are taking volume values, on y-axis pressure values are taken. Then we will get the curves. They are called isocurves. If this volume values are taken in this way, 1 by b, that is reciprocal of volume values are taken, then we will get straight line curve. Sorry, straight line in the graph. Why do we get straight line? Because pressure is directly proportionate to reciprocal of volume. So we will get lines in the graph in this way. So at temperature T1, this is the line obtained. T2, T3, T4. Here T4 is greater than T1, T2, T3. Okay, so that's about the relationship between pressure and reciprocal of the volume. So this graph can be asked for 1 mark. Now we'll move to second law, that is Charles' law. This law tells the relationship between volume and temperature. Means volume occupied by the gas is directly proportionate to temperature when pressure exerted by that gas and quantity of the same gas remains constant. So at constant pressure for a fixed volume or for fixed V proportionate to means fixed quantity. Fixed quantity of the gas, volume at constant pressure for a fixed quantity of the gas, volume occupied by it is directly proportionate to its absolute temperature. Absolute temperature means temperature on Kelvin scale, and it can be written like this: V is directly proportionate to T. Right? When proportionality mark is removed, we will get a constant, that is K, KT. Or it can be written like this also: V by T is equal to K, where K is proportionality constant. Next, if temperature changes, automatically volume occupied by the gas will also changes, and the expression will become V1 by T1 is equal to V2 by T2. Here also we have 4 terms. Out of these 4 variables, out of these 3, if 3 variables are known to us, the 4th one whose value is not known to us can be calculated. Now let us see the relationship between volume and temperature in the form of graph. Right? Temperature values are taken on x-axis and volume values are taken on y-axis. Right? Let this temperature be minus 273.15 and this is say minus 200 and this is minus 100. Right? We will get curves like this. structures in the graph. And this point refers to the volume occupied by the gas. In the case of Charles' law, at minus 273.15 temperature, volume occupied by the gas is 0. In reality, at 0 degrees centigrade, most of the gases cannot exist because they enter into a different physical state. Because of cooling, they enter into liquid form. So at minus 273.15 temperature, no gas exists and the volume occupied by it will become very, very less. That's about Charles' law. Thank you, children.